Section 4.3 is called Counting with Functions. A function is a one-to-one correspondence if it is both one-to-one and onto. So we have a theorem. Let the order of x be m, and let the order of y equal n. If a function that maps from x to y, if that function is a one-to-one function, then m must be less than or equal to n. So the order of x must be less than or equal to the order of y. If the function f that maps from x to y is an onto function, then the order of m must be greater than or equal to n. So the order of x must be greater than or equal to the order of y. This means if the function f that maps from x to y is a one-to-one correspondence, so if it's both one-to-one and onto, then to satisfy both of these inequalities, we must see that m is equal to n. And I encourage you to draw some maps, the ones we used with kind of the dots for the domain and the codomain and the circles, and try to map a one-to-one function, try to map an onto function, and make sense for yourself why the order of the domain and codomain must fit these rules. So let's look at an example. In a single elimination tournament, players are paired up in each round, and the winner of each match advances to the next round. If the number of players in a round is odd, one player gets a bye to the next round. The tournament continues until only 2 players are left, and these 2 players play the championship game to determine the winner of the tournament. In a tournament with 270 players, how many games are played? Well, let's let G be the set of all of the games played, and let L be the set of players who lose a game. We can define a function that goes from G, the set of all games played, to L, the set of all players who lose a game, defined by f of x equals L, where L is the loser of game X. So make sure you understand the function. We're inputting games and outputting losers. So we're outputting the loser of game X. Okay, since every game has a loser, the function is well defined. And since this is a single elimination tournament, 2 different games cannot have the same loser. Because if you lose once, you can't come back in to lose again. So this function is one-to-one. And since every loser lost some game X, this function is onto. Every loser has an input, a game, that maps to it. So this function is a one-to-one correspondence. It's a function that's well defined, it's one-to-one, and it's onto. That means the order of G must equal the order of L by the theorem on the first slide. So if we're trying to figure out how many games are played, the number of games is equal to the number of losers. So in a tournament with 270 players, only one winner. That means there were 269 losers, so 269 games played. The pigeonhole principle. The pigeonhole principle is the observation that if you put N pigeons into R holes, and if n is greater than r, so if the number of pigeons is bigger than the number of holes, then there must be some hole that has multiple pigeons in it. Try to put 3 pigeons into 2 holes, there's going to be 1 hole that has 2 pigeons in it. That is the pigeonhole principle. Mathematically stated, we're saying let the order of set X equal n and the order of set C equal r. And let f be a function that goes from X to C. If the order of the domain X is greater than the order of the codomain C, then there are distinct elements X and Y with f of X equal to f of Y. So looking here, the pigeons are where our domain is, and we're mapping into the holes. If there are more pigeons, i.e. if the order of the domain is larger than the order of the codomain, then there must be different elements. So for this map here, what do we have? Pigeon 1 and pigeon 4 both map into hole A. Pigeon 3 and pigeon 6 both map into hole B. So there are distinct elements in the domain that have the same output, the same hole, if we're thinking about pigeons and holes. In other words, we're saying this function cannot be one-to-one. The generalized pigeonhole principle. If you have way more pigeons than holes, you would expect to find some hole with a lot of pigeons in it. Mathematically stated, we're saying let the order of X equal n and the order of C equal r, and let f be a function that goes from X to C. If n is greater than r times L minus 1, then there is some subset U of X such that the order of U equals L and f of X equals f of Y for any element or elements X and Y in U. What we're saying, there is some hole that has L pigeons in it. So all of these outputs are the same. All X and Y are mapped to the same hole, if you will, for every X and Y in this set U. So before we can actually do examples with the generalized pigeonhole principle, we need to talk about the ceiling function. The ceiling function is represented by kind of a vertical line with a top bracket on it, but not a bottom one. That's representing the ceiling. There is something called a floor function where the bracket points downwards instead. But here we'll talk about the ceiling function, and what the ceiling function does is round the input to the next highest integer. For example, the ceiling function of 1.8 equals 2. It rounds 1.8 up to the next highest integer, which is 2. 1.1 in the ceiling function rounds up to the next highest integer, which is 2. So this is different than how you were taught to round in elementary school. 1.1 technically rounds down, but anything you put into the ceiling function rounds up. That's why it's called the ceiling. So 1.1 rounds up to the next highest integer, which is 2. And if you plug in an integer, then it gets to stay the integer that it is. 1, the integer that it would round to is 1. But if I had 1.00001, anything bigger rounds up to the next highest integer, which would be 2. Using the ceiling function, we can reword the generalized pigeonhole principle to say, let the order of X equal n, and the order of C equal r, and let f be the function from X to C. Then there is some subset U. u is a subset of x such that the order of u is equal to the ceiling function of n divided by r, and the outputs f of x equal f of y for any inputs x and y in u. So let's make sense of this with an example. A website displays an image each day from a bank of 30 images. In any given 100-day period, show that some image must be displayed 4 times. So we're going to let x be the set of days. We are looking at a 100-day period. So the order of x is 100. And let's let c be the set of images. And we have 30 images in the bank. So the order of c is 30. So there are a lot more days in this 100-day period than there are images. So if we define a function from the set of days to the set of images, defined by f of x equals the image displayed on day x. So we input days and we output images. The generalized pigeonhole principle says that if you divide 100 by 30, it would be 3.333, and take the ceiling function of that, 3.333 rounds up to 4, the generalized pigeonhole principle says there is some image that is displayed 4 times. Basically, if we only displayed every image 3 times, we would only be able to do that in 90 days. If we did a different one every day, and every image was used 3 times, that would be 90 days covered. But in a 100-day period, there's going to be 10 leftover days, so some image has to be displayed a 4th time. And we'll pick up in the next video with section 4.4.